Good afternoon. I'm Katherine Blundell, Gresham Professor of Astronomy. I'd like to welcome you to a new academic year of lectures on astronomy. And the title of this year's course is Cosmic Vision. Today, I'm going to be speaking about the radio universe. So for millennia, astronomy was, of course, solely a by-eye activity. As I described in the Gresham lecture I gave in May, this advanced in different cultures according to their perceptions and their expectations in remarkably different ways. Just over 4 centuries ago, in 1609, Galileo enhanced this by-eye vision with the development of the telescope, and that revealed Jupiter to have moons in orbit around it. Even by eye, if we are blessed with good eyesight, and if we're blessed with a night free of clouds, then we can easily see perhaps a planet or the moon from even urban locations where we might live. And this is the case even before the sun has completely set. Once the sun has completely set, and if we're in a part of the world that isn't light polluted, and when we are dark adapted, then we can hope to see quite a number of stars. Sometimes, if we are very well dark adapted, then we can discern different colours in some of these different stars. That is the case if we are blessed with 3 different types of cones in our eyes, which are sensitive to red light, longer wavelengths, green light, middle wavelengths, and blue light at shorter wavelengths. And of course, if we do have those 3 types of cones in our eyes, then we can admire rainbows, such as this beautiful example here, shown above the Australia School Observatory, which is part of the Global Jet Watch that I described in my 3rd Gresham lecture just before last Christmas. So a rainbow happens when raindrops disperse sunlight into different angles according to their colours or wavelengths. I have a number of friends who like photographing rainbows. One of these is Andrew Steele. And I was very struck by this particular rainbow, not just because of the beautiful colours it shows in the optical, but because of a montage that he made. For the exact same rainbow, he took his digital camera and he applied an ultraviolet filter, a UV filter, which blocked any optical light going through and only permitted the shorter wavelength ultraviolet light to get through, seen here in the white, i.e. the brighter band, at shorter wavelengths than we see in the blue-violet end of the rainbow. He then very rapidly put on an infrared filter onto his camera, and you can just see that extending at longer wavelengths as well. This triptych of the same rainbow gives us a big hint that there is more out there than what we can see with our own eyes. And there is, of course, a whole spectrum of electromagnetic radiation out there. It extends from the radio to the X-ray. We now understand that it's all exactly the same phenomenon, the only difference being the wavelength of those electromagnetic waves that comprise light. Now, optical light that, as I've said, our eyes are sensitive to, cannot penetrate through dust any more than UV light can penetrate through a sun hat. So if we want to look deeply into space and to see into the dust that is at the centre of our own galaxy, the Milky Way, we actually need to go to those longer wavelengths, at the very least into the infrared. So I'm showing here an infrared image of our galaxy, the Milky Way. And we can see right into the centre if we wind up the resolution, and we can examine in detail the paths of stars very, very close to the galactic centre. Now, in fact, this is exactly what Reinhard Genzel did, studying the galactic centre at infrared images and tracking with time-lapse imaging the paths of stars moving at the very centre of our galaxy. He and Andrea Ghez, working at UCLA, calculated the orbits of stars around a seemingly dark point at the very, very centre of our galaxy. Thanks to their work, we now understand that there is a black hole, which is the focus about which those stars are orbiting. And we now know, thanks to their work, that that black hole has a mass of nearly 4 million times the mass of our sun. And so it was a great delight just yesterday to see that their work had been honoured with a Nobel Prize in Physics, along with my colleague at the University of Oxford, Roger Penrose, for his work on how black holes are predicted by Einstein's equations within general relativity. So let me take you back 1 year ago. Those of you who watched my inaugural lecture will have heard my discussion about can we go faster than light? And I described the work of the Scottish physicist James Clerk Maxwell, who made a prediction of exactly what the speed of light ought to be. In the early 1860s, he made the remarkable prediction that the speed of light had a very pure dependence only on the magnetic properties and the electrical properties of the space that electromagnetic radiation was passing through. Maxwell figured out that light was an electromagnetic wave that behaved and obeyed some powerful equations even before the USA had abolished slavery. Part of the importance of the work of James Clerk Maxwell is that he established there were no length limits to which his equations applied. In essence, he predicted the existence of the radio waves and the X-rays that are longer and shorter wavelengths than the optical light to which our eyes are sensitive. So that prediction was in the 1860s. But I want to take you a bit closer to where we are now by a couple of decades to the work of the German physicist Heinrich Rudolf Hertz, who actually demonstrated the existence of radio waves. So he connected up to the apparatus shown at the back of this figure a very high voltage, and that caused there to be sparking across the gap seen at the back there. That sparking, in turn, generated variable electromagnetic waves, and these then induced a current at the rather more distant ring seen at the front of this image. Once a current was induced, then a spark jumped across the gap. In that action at a distance, he had demonstrated the existence of electromagnetic waves whose wavelength he could demonstrate to be centimetres and metres according to the experiment that he was performing. He could demonstrate that their nature was to reflect and to refract in exactly the same way that the optical light we are so familiar with behaves. So thanks to the work of the predictive work of James Clerk Maxwell and the experimental demonstrative work of Heinrich Hertz, we knew almost a century and a half ago that both visual light and radio waves are electromagnetic radiation. This led to some important developments in communication, and bad and ghastly and awful though the disaster of the Titanic sinking was, it would have been far worse had it not been for radio communications. 108 years ago, that April night, that moonless night, after the Titanic hit that fateful iceberg, it is thought that radio communications prevented the loss of life being worse still. Sending CQD and SOS messages at 500 kilohertz, Hertz being named after Heinrich Hertz, of course, this is 600 metre wavelength, from the Marconi cabin within the Titanic. Other ships carrying radio communications were alerted, and they told other ships still, and they were able to locate where the Titanic was sinking. And it's thought that maybe some 700 lives were saved thanks to radio communications, thanks to Hertz and thanks to Maxwell. Well, more recently, but still back in war times, radio communications provided a vital role. Chain Home, which was the first early warning radar network in the world, was built by the Royal Air Force before and during the Second World War. And it's been said, not least by Winston Churchill, that radar played a crucial role alongside the brilliance and the bravery of the fighter aircraft pilots and the engineers in winning the Battle of Britain. Now, radar clearly didn't just have uses for communications on this planet. And some 87 years ago, Karl Jansky in the US built a contraption, a construction somewhat resembling the radar antennae, mounted it on something that got referred to as a merry-go-round, and he used this to study radio signals from different viewing angles. He investigated this deeply, he understood different sources of radio signals, and in the end, he concluded that radio signals were coming from outside of the planet and were thus extraterrestrial in origin. So the New York Times announced that these new radio waves discovered by Karl Jansky had been traced to the center of the Milky Way that I was showing you in that earlier infrared image. This is the paper that he wrote. This paper was submitted to the proceedings of the Institute of Radio Engineers. Now, I think it's fair to say that it took the world of radio astronomy a little while to get going, because radio engineers, electrical engineers didn't know anything about astronomy, and astronomers certainly didn't know anything about electrical engineering. But nonetheless, progress happened and made important strides. So in Illinois, Grote-Reber built a rather fancier, more sophisticated-looking radio telescope, somewhat more resembling the dishes that we might see today. And in this seminal paper, he pinpointed the area that these radio waves, first discovered by Karl Jansky, were coming from, definitely to the constellation of Sagittarius, known to be where the center of our galaxy is in the skies seen from planet Earth. It strikes me as rather amusing that the title of this paper, Cosmic Static, demonstrates that this paper was published long before spin doctoring had been invented. So let me show you the data that Grote-Reber got from this single antenna in Illinois. This is a projection of the sky, and in that very central region, in that enclosed group of contour lines, is indeed the center of our galaxy. Let me just make the comment that this contour representation is a way of representing what's brighter and what's less bright on a particular image of signals that you're detecting. So the more a particular contour is surrounded by other contours, the brighter that region is. And so the bit that I'm talking about is this region here. This is the center of our galaxy. This is the constellation of Sagittarius, beaming brightly in those radio signals. Now, radio telescopes have advanced hugely since then, and one that jumps to mind immediately is the Lovell telescope, hosted at the Jodrell Bank Observatory in Cheshire. This is a very sophisticated instrument. It's part of the Merlin network that gives us very fine detail on radio images in the sky. It's actually now a UNESCO heritage site, and I warmly recommend a visit to the Jodrell Bank Discovery Centre once pandemic lockdown permits, of course. So this is a radio telescope, a very important radio telescope in the United Kingdom, but perhaps the most famous radio telescope at present is over in the United States, in New Mexico, in the southwest United States. I'd just like to make it clear that despite what you see in the Hollywood film, which starred this telescope along with Jodie Foster, I really would like to point out that we don't listen to radio waves. We don't use headphones, despite what the Hollywood films tell you. Nonetheless, I would like to commend this as a great movie to watch. This particular radio telescope has delivered some fabulous insights and images into the sky, which I will share with you presently. It consists of a collection of different dishes, collectively acting as one great big telescope, giving us fine detail, even on phenomena that are very distant from Earth. And you can see perhaps 4 of these telescopes standing against the majestic Milky Way, this image being taken with just a normal digital camera, albeit by a very skilled photographer, a friend of mine, Drew Medlin. This next photograph, also of the Very Large Array, the VLA radio telescope, similarly showing the plane of our galaxy, also demonstrates one respect in which radio astronomy is superior to optical astronomy, which is that you can carry on even when the clouds are gathering. And that's enormously helpful. Clouds are really bad news for optical astronomy, of course. But in radio astronomy, because the wavelength is longer, clouds are transparent. So back to the optical sky, and let me take you to an area of the sky called Cygnus. This is very well known. Wherever we see a little dot of light, probably you're looking at a star. Wherever we see these optical points of light, wherever we see these stars, that's telling us about where fusion is taking place in the universe. Stars shine because of fusion. But not all of the points in this image are stars. The thing at the very center is a fuzzy blob, itself a coagulate of very many stars. So that's the view at optical wavelengths. Let me now remind you of what it looks like at radio wavelengths. And this is on the same angular scale. It is a completely different picture. You can see that squirting out in opposite directions from this central point, which is at the very center of that fuzzy galaxy of stars shown in my previous image, we see jets of radio-emitting plasma, which are themselves launched from the vicinity of a black hole. They transport extreme amounts of energy way beyond the confines of that host galaxy into the intergalactic medium. The size scales here are huge. The length from one end to the other is in excess of 100,000 light years. Let me remind you that a light year is a unit of distance. It's the distance that light can travel in 1 year. And as discussed in my very first Gresham lecture, the speed of light is astoundingly fast. So 1 light year is an astoundingly long distance, and 100,000 times that is 100,000 times astounding. Roughly speaking, the timescale for it to grow, for this structure to grow to this sort of size, is in excess of 1 million years. And as I say, this all emanates away from a central black hole, whose mass is something like 1 billion times the mass of our sun. Jets are prevalent in our universe. We detect them readily at radio wavelengths. When we look at a radio picture like this, not only do we see evidence of this energetic transport impinging on the intergalactic medium and shocking and giving rise to particle acceleration, but it tells us about the presence of magnetic fields in the universe. It tells us about the presence of highly energized charged particles, electrons and protons, which themselves are traveling at speeds close to the speed of light, this astoundingly fast speed discussed in my inaugural lecture. They are invariably characterized by jets moving in opposite directions, huge amounts of energized plasma squirting in opposite directions, way outside the confines of the host galaxy shown here in blue. This red light is, this red brightness is telling us about how bright the radio emission is at a wavelength of about 6 centimeters, vastly longer than the optical wavelengths at which we see the host galaxy. The person who imaged these, my friend Robert Lang, has made some exquisitely detailed studies of these jets, and it's remarkable to be able to zoom in these and admire the features of jet ejector puffing and powering through the intergalactic medium. They are remarkable, and they speak of immensely dynamic and explosive processes, all emanating from those exotic phenomena known as black holes, which I described in my third Gresham lecture just before Christmas last year. These objects are known and can be demonstrated to expand at great speeds, at speeds which are themselves comparable to the speed of light. And because they have a very, very long life cycle, in excess of millions of years, they grow to huge sizes. I'd just like to demonstrate to you with this particular radio quasar that just how large these sizes are. So the green shapes that you can see here correspond to where the two jets emanating from this host galaxy with its own black hole have impinged on the intergalactic medium here and here. If you zoom in on this lower region here, this lower hotspot as we call it, where there's a great big shock, where that energetic jet impacts on the intergalactic medium, then we see remarkable detail. The blue contours here are still at radio wavelengths, and that particular fine resolution image was made with the help of the Merlin network and the Lovell telescope that I mentioned from Jodrell Bank. But the red pixels here are now telling you about emission as measured by the Chandra satellite, which is sensitive to the very short wavelength, very energetic emission in the X-ray waveband. And we were able to study some of the energetic processes when these great big quasar jets squirted out of the black hole and then impacted on the intergalactic medium. I said I'd tell you about the size scales that we're talking about here. And what we're talking about from end to end is something like 36 million light years. On that little bit that I zoomed in with the help of the Jodrell Bank telescope and the Chandra X-ray satellite, we're talking about 65,000 light years. Now, for those for whom light year is not a very familiar unit of distance, let me try and offer a different calibration. If you try really hard in the gap between this sub-shock structure within that hotspot of that large radio structure, you can stuff in 3 Milky Ways, providing you sandwich them in sideways. That's how large these radio structures are. We miss out on the immensity and the extreme nature of these objects if we're confined to only looking at what we can see with our eyes. So let me point out that the influence that these radio quasars have is vastly in excess of the event horizon of the black hole, which gives rise to these phenomena. They are absolutely remarkable structures, and they redistribute heat and energy in the intergalactic medium, affecting the formation of structure, affecting the formation of galaxies themselves as they do so. Again, let me emphasize how prevalent these objects are in the night sky. This is a particularly fine example in the southern sky, imaged by friends Alana Feehan, Tim Cornwell, and Ron Eakers. This extends over 6 degrees, and just to give you a bit of a perspective on how big that is relative to some more familiar things that we see in the night sky with our own eyes, that's the moon there, and with those radio telescopes and a few trees in the bottom of the image, just to give a sense of how big this structure is. Imagine if we could see that with our eyes. I think we would be even more awestruck by the night sky than perhaps we already are. Now, I've mentioned that these radio structures can take in excess of millions, sometimes even hundreds of millions of years to grow to the sizes that they are. The downside of that is that we can't see them evolve gradually step by step. We can't follow their life cycles step by step. But nonetheless, deep, high-fidelity imaging with modern radio telescopes means that we absolutely can study and investigate some of the plasma physics processes and some of the astrophysical processes and effects that they have on the surroundings into which they expand and grow. This particular example that I'm showing you is a very fine example, imaged by my friend Bill Cotton at NRAO. Before this high fidelity, high detail, high resolution image was made, people wondered, with perfect validity, it was a very sensible suggestion, could it be that these regions here were a previous indication of a former jet direction, whereas this is now the current one, or the other way round? But thanks to this high fidelity image, it now seems much, much more likely that as the initial powering of the jets in that direction happens and then material flows back, it has to divert because there's no other space for it to expand into. So we can make really good progress by analysing these sorts of images in great detail and reflecting on the energies and the astrophysical processes that are taking place. Let me show you another very beautiful example. This object is known as Hercules A, and the radio emission here is represented in the pink. The background of different stars and different galaxies is at optical wavelengths. It's imaged by the Hubble Space Telescope. And against that Hubble Space Telescope background image of various galaxies, this is a galaxy, this is a galaxy, this is a galaxy, this one is a star, this one is a star, and this one is a star, we get a sense of the immensity and the grandeur of such a radio structure emanating from yet another black hole in the galaxy. And this image bears fruit in response to detailed investigation and study. You can see these successive balloons being blown. And over here, on the left, you see evidence perhaps of the jet wiggling around. And there are different reasons why that might be occurring. It might be inhomogeneities in the density into which that jet is trying to power through. Let me remind you, empty space is not empty. Or it could be that maybe that jet axis is wandering because of processes that are going on in the vicinity of the event horizon surrounding the black hole itself. So, as I've indicated, it can be a little bit tricky to try and drill down and understand very definitively what the processes are that give rise to these very beautiful radioplasma structures, but we can make intelligent strides in progress, and we've learned a huge amount about how these phenomena evolve. But turning back now to our own galaxy, to the Milky Way, and thinking about radio jet sources within our galaxy from Milky Ways, from black holes within the Milky Way, that is a very, very complementary way of studying these radio jet phenomena. And so let me show you an image that I talked about a little bit in my third lecture before Christmas, which was all about black holes and considering whether they marked the end of matter. The answer to that question was no, by the way, as evinced by the beautiful structure that you can see here. I made this image myself some years ago using the Very Large Array radio telescope. And it was one of those moments when I made the image when you practically fall off your chair in awe at the beauty of this amazing astrophysical structure. We've now, this is together with Robert Lang, whom I mentioned earlier, got out a whole lot further. But that's another story for another day. But I want to give you a sense of how on earth we can end up with radio structures that are that shape. This is a radio image where the different colours represent how bright the different parts of the radioplasma are. So blue is relatively faint, green is brighter, yellow is brighter still, and red is the brightest on this particular image. And so you can see that the brightness levels fade as you get further and further away from that central launch point coloured in red. But still we see very clearly in green first and then in pale blue. On the left, a very striking zigzag shape, and on the right, a curly corkscrew shape. How on earth does that come about? Let me remind you, this image is part of science fact. It is not part of science fiction. It is for real. If our eyes could see at radio wavelengths, we would see things that shape. How does it come about? It comes about because the direction along which those radio jets squirt out changes in time, like the paddle of a kayakist in its own rest frame. Let me show you a little cartoon of this. I've shown you this before in a different context in that third lecture. What I've done here is to colour code material coming towards you blue, material moving away from you red. There's something remarkable about the speed at which that's encoded in the way this is moving, which I'll come to later. But an important point to realise is that once plasma is launched from that central launch point near the black hole itself, it's thought to travel ballistically, that is to say it suffers no deceleration, no acceleration, and it just persists further out. Some people find it easier to look at the simulation in this way. If you consider pairs of blobs of plasma launched in anti-parallel directions, just absolutely moving very, very steadily with time, but each one launched in a slightly different direction compared with its neighbour and with the succeeding pair of plasma blobs. I mentioned the importance of the speed at which that plasma is launched on the detailed appearance of this structure, the fact that it's zigzaggy on the left, the fact that it's curly corkscrew on the right. Now, in fact, if the speed at which that plasma is launched is at all comparable with the speed of light, then we get a very strong dependence of the shape of that structure on the speed at which the plasma is launched. And let me show you now a different movie, a little bit similar to the ones I've just shown you, but what I'm doing now, instead of showing you how that radio structure would look if we could observe it with a radio telescope for a period of 6 months, if we could colour code the plasma moving towards us blue and moving away from us red. I'm doing a different variant of that movie now, fixing the phase of that cycle, but what I'm doing is to change the speed of launch. So hold on to your hats. This one is different again. So you'll see that I'm recording the speed down in the bottom left. I'm actually changing the distance at which this object is away from Earth just to preserve the angular scale on the screen. Otherwise, the two ends of this would end up in opposite sides of London. So I am scaling the screen, the image on the screen, to allow for the fact the speeds are getting faster and faster. And you see that as we get to higher and higher speeds, the asymmetries in this structure become more exaggerated and more profound. Material moving towards us gets much closer to Earth much more quickly. Material moving away from Earth goes in the wrong direction, but all the light received from those corresponding points are received at the same telescope time. And so the details of the pattern that we see depend crucially on light travel time effects, in a sense, on special relativity itself. So I hope that gives you a sense of how we get to this radio structure looking the way that it does. I talked about this object, this microquasar, in some detail in my third lecture from the perspective of optical spectroscopy, studying the material as it's launched very close to the black hole. But it's equally rewarding and equally good fun to study how the radio plasma extends away from that central launch point of near the black hole. Let's return to some extragalactic radio sources now, and I want to return to that beautiful radio galaxy in the constellation of Cygnus. It's known as Cygnus A, and it's such an important object in the world of astronomy that even boats have been named Cygnus A in its honour. So what I'm showing you here in blue now is that radio plasma that I showed you earlier in the black and white image, giving us those dumbbell shapes of radio-emitting plasma. What's shown here as red-orange is actually X-ray emitting plasma. And that X-ray emission is again measured by the Chandra X-ray satellite operated out of Harvard. Let me talk a little bit about why we get such a different picture from the same astrophysical phenomenon. As I mentioned earlier, radio waves have to do with electric fields and magnetic fields. Where you see radio emission in this sort of object in the universe, that is tracing where you have magnetic fields. At the same time as having very energetic charge particles, such as split-up hydrogen atoms, electrons, and protons. Those get accelerated to extremely high energies because of what happens when those jets blast out and crash into their surroundings. But at the same time, there are lots of heating processes that are taking place, and that helps give rise to some of the X-ray emission that's much closer to the deep potential well, at the heart of which is that black hole that, as I remarked earlier, has a mass 1 billion times the mass of our sun. Where we see X-ray emission, that tells us about the presence of gravitational forces attracting matter in. It traces very, very high temperatures. The gas that we're seeing here, indicated in red, is at temperatures in excess of 1 million degrees. And I'm not specifying whether I'm talking about Kelvin or degrees Celsius. When you're talking about the kind of energies that give rise to astrophysical X-ray emission, it doesn't matter too much which temperature scale you're on. We start to calibrate in the energies in other ways. Now let me zoom in just to this radio dumbbell on this right-hand side of the image. So again, I'm still showing radio emission with a wavelength of about 6 centimeters. And you can see the central nucleus, this dot here, is the location of the black hole at the heart of that host galaxy, that fuzzy blob that I showed you towards the start of my talk. This brightness here is telling you about the jet that is curling around in a direction that ultimately leads to those bright shock structures. If I start overlaying straight lines, shown here in green, I hope you can get a very strong sense that that jet is waving around. And some years ago, Katherine Steenbrugger and I fitted the exact same model of precession to the jet in Cygnus A that I showed you for the previous microquasar, the zigzag curly corkscrew one, where we found, for that zigzag curly corkscrew one, we found that the precession period was a bit short of 6 months. The precession angle was about 20 degrees. In the case of Cygnus A, we found that the precession angle was just about 1.5 degrees, but the precession cycle, the time cycle, the periodicity of the precession, forget about 6 months, it was just a little bit short of 1 million years. So very different phenomena. On the one hand, within our galaxy, the Milky Way. On the other hand, extragalactic, magnificent, supermassive black holes, giving rise to these immense, majestic, slowly evolving, but highly energetic structures. Well, the VLA continues to enrich our understanding of the universe, of the radio universe. But let me talk a little bit about some of the exciting new technologies which are emerging in different parts of the world. So let me take you to the Karoo in South Africa. And I'm showing here an image, again, a collection, an array of different radio telescopes, each one individually somewhat resembling that early radio dish of Grote Reber, who made the first image of the Milky Way, which I showed in contours earlier. And here in the Karoo, this collection of radio dishes, all acting together as one great big radio telescope, gives us a very sharp, very high resolution view of the southern skies. This beautiful image by Roger Dean, shows the entirety of this array of radio antennas. Each white dot here is one of 64 radio antennas, and collectively they comprise a telescope whose name is Meerkat. Well, the inauguration of this took place a couple of years ago, and you can see with these humans for scale some sense of the size of each one of those 64 radio antennas. The diameter of one of these radio telescopes corresponds roughly to the size of Bernard's Inn Hall from where I'm speaking to you today. You couldn't fit one of these radio dishes into this hall. It would damage the woodwork terribly. But that's the kind of size scale that we're talking about, and with 64 of them, that's a tremendous advance to have lots of collecting area, able to see very sensitively into the deep radio universe. There have been some spectacular images from the Meerkat telescope. The importance of the Meerkat telescope is not just in the amazing images it has delivered just within 2 years of its inauguration, but also the fact that it's a pathfinder, it's a prototype of one of the other next generation telescopes known as the Square Kilometre Array, which is going to be partly based in South Africa and partly based in Western Australia. So let me show you some of the beautiful images from the Meerkat radio telescope itself. So this image, I hope, reminds you of some of the double radio sources that I showed you earlier in my talk. So just to explain here, the wavelength here is about 20 centimetres. Purple is the fainter radio emission, orange is a bit brighter, yellow is brighter still. So that represents how loud or how bright that brightness, different parts of the brightness distribution is. You can see exactly where the jets launch from their black hole there, always in anti-parallel directions, and you can see that plasma flowing back from those, sometimes in familiar ring structures. But what's remarkable about this image is the fact that you see streaks, linear streaks, which almost resemble lightning, as charged particles streak across from one part of space to another. If you think lightning is frightening, trust me, you wouldn't want to be anywhere near this object. So this beautiful image was made using data from Meerkat by Mpati Ramatsuku when she was at Rhodes University. And it's a terrific image that's given us new insights into how these beautiful radio galaxies evolve. These multiple, highly collimated linear threads tell us that actually these radio lobes are connected by the presence of electric fields, perhaps, that would otherwise be unseen without the sensitivity of a telescope that is sensitive in the radio window. Just to give you a sense of scale here, the most prominent of these radio threads, this one reaching across here, is about a couple of 100,000 light years long and about 3,000 light years from one end to the other. Space is a violent and a dynamic and an explosive place. Zooming out now, not just looking at one individual radio galaxy, I want us to return to the centre of our galaxy and to show you an image that was made by my friend and colleague in Oxford, Ian Hayward. So this is his image of the centre of our galaxy. This image corresponds to a spatially resolved version of the cosmic static imaged by Grote-Reber 76 years ago. And it was wonderfully finished in time for the inauguration a couple of years ago. And even just with this relatively wide field zoom, you can again see all sorts of highly collimated streaks which emanate away from the plane of our galaxy, at the same time as seeing lots of little loops or circles in projection corresponding to the remnants of supernova explosions. I'm going to zoom in a little bit just so that you can I hope, see some of the exquisite detail of the distribution of radio-emitting plasma in the centre of our galaxy. So this very central image here, referred to as Sagittarius A star, actually has, at its very central point, that 4 million solar mass black hole that Andrea Ghez and Reinhard Genzel worked so hard to determine over the last decade and a half or so. And there's all sorts of radio fireworks going on in that vicinity. This one, amusingly, I don't know if you can see, but it's a double radio source that's actually in the far background, far away from our Milky Way galaxy, that we can just about discern through all the radio-emitting plasma that's coming from the plane of our own galaxy. I strongly encourage you to look for some of the Meerkat images on the Meerkat website. They are truly beautiful, and just examining them in great detail will, I'm sure, inspire a great sense of awe into the richness of the radio universe. Again, these two bulges have their origins in the remnants of supernova explosions, and some of these little streaks correspond to stars that have a very significant proper motion. For some reason I'm not entirely clear of, this was nicknamed the mouse. It's nothing like a mouse, not in energy, not in size scale, and I've never heard of a mouse that in real life emits at radio wavelengths, just in the optical. Well, I now want to zoom out further still, while still looking at our own Milky Way galaxy. Again, this is another beautiful Meerkat image made by my friend Ian Hayward and his co-workers. So the bright orange-red emission that I was just showing you from the very centre of our galaxy actually corresponds to about here. So this is a really wide-angle view of the plane of our Milky Way galaxy, which I showed you at infrared wavelengths towards the start of my talk. And I wonder if you can make out the fact that there's something of a bubble structure. Where it's dark here, that's an absence of radio emission, but you can see that there's a rim that delineates the shape of two seemingly oppositely directed bubbles. That's a characteristic signature of the fact that jet ejector snowploughed out and cleared out gas from that sort of region, accelerating and energizing the surrounding plasma as it did so. Again, the size scales that we're talking about are absolutely huge. So I'm now going to overlay a picture of the Meerkat telescope on this background, and I hope that it gives a sense of just how large structures in the radio sky can now be imaged thanks to modern technology. It is an absolute technological triumph for all of the engineers and all of the astrophysicists involved in creating such a beautiful structure, a beautiful image of the structure within our Milky Way galaxy. So doing astronomy at radio wavelengths does indeed give us a new window on the universe. It reveals dynamical structures and extreme energies, and sometimes explosions, as indicated by these supernova remnants here. Beyond all that we're learning about the universe at radio wavelengths today, radio waves continue to play a very important role here on Earth. For example, with radar in aviation and in communications. And while we remain in the grip of a pandemic, we are indeed blessed that we can communicate with electromagnetic radiation at radio wavelengths, thanks to a very important advance in radio astronomy that, if the pandemic had happened 25 years ago, without that, we would not have been able to communicate with one another. It is thanks to the expertise and the persistence and the imagination of some radio engineers in Australia, led by John O'Sullivan, and astrophysicists who were pursuing the signal of merging black holes that we ended up with Wi-Fi, wireless communication, the 802.11 protocol, that means that we can be connected over the internet even during these pandemic times. So the radio waveband of the electromagnetic spectrum is a wonderful place to study things beyond our planet, and it's a fantastic means by which we can communicate with one another all around this planet. Well, with apologies to the Scottish hymn writer, Walter Chalmers Smith, I do often find myself thinking of one of his hymns as being truly inspired and appropriate for radio astronomy. It's talking about that which is invisible and light inaccessible, hid from our eyes. This hymn was written just about 2 years after James Clerk Maxwell predicted the existence of radio waves. And I do hope that in the brief tour of the radio universe that I've been able to give you this afternoon, you will agree with me that if we confine ourselves to only that which is visible to our eyes, we miss out on a huge amount. And so that concludes my lecture for this afternoon on watching the radio. Thank you.
Professor Blundell, thank you very much for a really, really interesting lecture. Our online audience found it compelling as well, and there are a few questions for you. The first one is, how do the radio waves get converted to the coloured images?
That's a very good question indeed. You may have noticed at certain points in my talk I was saying things like, where you see purple, that's fainter radio emission. Where you see orange, it's a bit brighter. And where you see yellow, it's yet brighter still. So what you do is you do some kind of colour mapping. You define a colour scale where you say, if it's not very bright, if it's fairly faint emission, we'll map it to this colour, purple in the case of one of the examples I showed towards the end of my talk. If it's a bit brighter still, then we colour it orange. If it's a bit brighter still, then you colour it yellow. So you have to come up with some kind of mapping. Our eyes are not, obviously, as has been a theme of this talk, sensitive to radio radiation. So we need some way, some scheme of saying what's brighter and what's fainter. Human eyes are really pretty good, usually, at recognising and understanding different colours. It can also work fairly well. They're to work in monochrome, meaning black and white and grey and so on. And the first image that I showed you of Cygnus A in this afternoon's lecture was such an image. And in that image, I think white was the background, the very faint information. Light grey was not quite so faint. Deeper grey was brighter still, and then the black emission was the really strong, powerful stuff, the stuff at the outermost edges of that radio structure. So you have to come up with some suitable scheme. There's no unique scheme, there's no right scheme of doing it. And so it's very important to describe carefully how you are actually doing that mapping. It's fair to say that sometimes we do, particularly in astrophysical analysis, because of the vulnerabilities of relying on colours that work well for some folk and less well for others. Sometimes in our astrophysical analyses, we'll use contours to represent what's bright and what's not. And so if you were to look at one of the contour images of Cygnus A, you would see those very bright outermost regions, being surrounded by loads and loads of contour lines. And that's a different kind of representation to say, this bit's really bright, this bit's not so bright. So there's no one unique way of doing it, but those are the two we most commonly employ.
Thank you. Where does the energy come from to produce the giant jets?
Oh no, that's a great question. The ultimate answer to that is, in fact, gravity. So matter, as I described in my third Gresham lecture before Christmas last year, nearby a black hole has a lot of gravitational potential energy. The gravitational attraction of the black hole on that matter sucks it in. And so it's moving at great speeds. But as I described in that lecture, the law of gravitational attraction is not the only law that is operating. We also have the law of what I described in that lecture, the law of conservation of angular momentum, which means that if things are spinning too fast and they can't go any faster, then they squirt out. Ultimately, that energy, which gives rise to the acceleration of the plasma, the particle acceleration at the outermost edges of the jets, it all goes back to that amazingly compact region at the heart of it all, the black hole, and its gravitational activity.
What would the advantages of a radio telescope be if it could be built on the dark, far side of the moon?
Oh, now that's a great question. Whoever asked that question, I would love it if we could build a telescope on the far side of the moon. It's not quite correct to call it the dark side of the moon, because actually when we have a new moon, the far side is fully illuminated by the sun. But the point of the question is, if you put a telescope on the far side, a radio telescope on the far side of the moon, why would that be a good idea? It would be a great idea because you wouldn't be subject to some of the problems that occur for radio telescopes here on Earth. So, as I indicated in my talk, for the most part, radio telescopes here on Earth can breeze through and operate as normal, even when there are clouds overhead. But where radio telescopes struggle is with the ionosphere and the troposphere that surround our planet, the magnetic fields and the particles that, many of which come from the wind from our sun. The ionosphere and the troposphere hinder the ability to do radio astronomy at very long wavelengths, at wavelengths tens of meters in extent. If you've got an ionosphere, you can't do that kind of astronomy. As I talked about in one of my earlier lectures about a year ago, the moon doesn't have an atmosphere. We don't believe it has a strong magnetic field. We don't believe it has much in the way of an ionosphere. So if you could put a radio telescope on the furthest side from Earth, then you'd be able to do some fantastic observations in a slightly different waveband still compared with the radio window that I've talked about this afternoon. You'd be able to look at longer wavelengths, and that would be great.
There were some wonderful images of rotating stars at the beginning of the lecture. Everything is rotating, but relative to what? What determines the fixed frame to measure it against? If it is the distant stars, how is that averaged? And if they weren't there, if it was only the sun and the earth?
That's a great question too. So the images that I showed, I think I showed a movie from Reinhard Genzel, and then I showed a schematic picture from Andrea Ghez, the Nobel laureates from just yesterday. The fixed frame in this case is really the plane of our galaxy. So if you imagine that image has been taken while the centre of our galaxy, while Sagittarius moves through the sky, the telescopes in question have tracked that. So it's only very, very close to the centre of our galaxy. Those images were a real zoom in. It's only very, very close that those stars are whizzing around. What they're whizzing around is something of a fixed point compared with the galactic plane itself. It's the black hole at the centre of our galaxy that Andrea Ghez and Reinhard Genzel discovered. So it is all done jolly carefully, and the sun and the moon don't come into it, the sun and the earth don't come into it. Whenever you're doing observations of any kind, be it radio observations, be it optical observations, you absolutely have to take into account things like how fast the Earth is moving along the line of sight to the particular science target that you're studying. If you're moving towards it or something like that, then your frame of reference is going to get very confused. So we absolutely correct for what we call that heliocentric motion.
Just two more questions. How does a shock wave form when the density of interstellar matter is so low and particle separation is so large?
That too is a great question. So a shock wave forms when you get a discontinuity in the densities of the gases or of the plasmas in question. Now, I think what the questioner is alluding to about the low density of space is something that can trouble people who are thinking very much about the sort of values that we get for shock waves here on Earth. As I said in my talk, empty space is not empty. And although the densities are very, very low compared with the density of our atmosphere, for example, they're not so low that all the laws of shock physics that we understand from studies here on Earth don't apply in exactly the same way. Various things are scaled differently. The size scales are much larger. We're talking probably hundreds of light years, if not 1,000 or more. Those density discontinuities are enough to cause the kind of shock physics that give rise to particle acceleration. It's a real thing. We see shock acceleration happening in the real universe, both within our galaxy and in the extragalactic examples, such as the ones that I showed.
And the final question, compared to optical astronomy, does radio astronomy allow us to look further back in time towards the Big Bang?
That's a very good question, and there are a number of facets to the answer of that. So, as I alluded to earlier, radio waves can see through dust in a way that's superior to the way that infrared waves can penetrate through dust, in a way that optical wavelengths simply can't. Optical waves cannot penetrate dust at all. Radio waves can do so really well. So if you've got very distant galaxies that are very dusty at their hearts, or for quite a lot of their, the entirety of their structures, radio telescopes can pick those up, whereas optical telescopes might absolutely miss them. So in that sense, we can see further back to the Big Bang. But there's another source of radiation in the night sky, or in the sky, I should say, to which radio telescopes are sensitive. And that's the radio emission from what we call the cosmic microwave background radiation. This is a signal at radio wavelengths, a little bit shorter in their brightest point than the wavelengths I've been talking about today, so we're talking more about millimeter wavelengths, that has its origin in the Big Bang itself. If you study its spectrum, if you study its uniformity in different parts of the sky, that's a radio signature that gets us back closer towards the Big Bang. Closer, but not that close. The cosmic microwave background radiation is only really telling us about the nature and the characteristics of the universe some 100,000 years after the Big Bang. So radio astronomy definitely gets us closer than optical astronomy, but not as close as we'd like.
Well, thank you very much, Professor Blundell, for a wonderful start to the series. And thank you to our audience. The next lecture that Professor Blundell will be presenting will be on the 28th of October at this time, the next lecture in the Cosmic Vision series. So please do join us for that. Thank you.